Now we come to the analytical solution of the LCR circuit. Okay, analytical solution of the LCR circuit, correct? You must be aware that till now whatever we had done was the graphical solution of it, the phasor diagram solution of it. Now we come to the analytical solution of it. Let me again draw that circuit diagram, and this is R and this is C and this is L. This is R, this is C, this is L, and this is, as usual, Vm sine omega t. Okay, this is Vm sine omega t. And as I had told you, let us say when the voltage is like this and the current is like that, then what is the equation that we'll be writing? What equation will we write? We'll write that by KVL we have, what do we have by KVL? Vm sine omega t, correct, minus IR, this will be some plus Q here and minus Q here, so, and this is a drop, so minus Q upon C, is it not, minus L di by dt. This will be positive, this will be negative. Why? Because the inductance would not like the flux through itself to be changed. So if you are trying to push a current like that, it'll create a voltage like this positive, this negative, so it is pushing like that. It does not want you to change the current through it. Fine? So inductors behave like that. So it is this which is equal to 0. I had started from here, from negative to positive, so I took this as positive. Then there were positive, negative, so there was a drop, there was a drop, there was a drop, negative, negative, negative is equal to 0. I have reached back to this point. KVL says the total potential drop around a loop is equal to 0. So what happens? So it gives me that L di upon dt, is it not, plus IR plus Q by C is equal to Vm sine omega t. Now I have to find out the current, correct? I have to find out this I. That is what we are supposed to do. This is given and I is supposed to be found out. Now there is a trouble. This involves I as well as Q. Fine? The solution will come only when you express it in terms of one and only one variable. Now for that, I know that I is equal to dq upon dt. I is equal to dq upon dt. Fine? So we know this. Thus, di upon dt is equal to d2q upon dt square. Is it not? Di upon dt is equal to d2q upon dt square. Now, what I am trying to do, I am trying to convert even the variable I in terms of q, so that I will have only one variable. So if I put these values in 1, from 1 and 2, we get what do we get? We get L, in place of di upon dt, I am putting d2q upon dt square plus r into dq upon dt plus q upon c is equal to Vm sine omega t. Okay, it is equal to Vm sine omega t. Do we understand? So it comes in terms of one variable. Okay. Now, there are various ways of solving a second order differential equation. Fine. This is a second order differential equation. Fine. There are several ways of solving these equations. One of them being Laplace transforms, which you will be taught later, and it makes a very easy job of this. Fine. But at our stage where we have not been taught to handle a second order differential equation, even in maths we have been dealing with the first order differential equation, correct? We are dealing with first all the three types that you dealt with in maths: the variable separable, the homogeneous, and the first order linear differential equation. They were all first order equations. So what I do here, we assume, see, if the cause is a sinusoid, the effect, that means the flow of the charges, will also be a sinusoid. Okay? If the cause, that is voltage, is a sinusoid, the effect that is the charge is also a sinusoid. Is it not? Obviously, so I know that thus Q is equal to Qm sine omega t plus theta. You know, it is not essential that the effect is in phase. We have been seeing that, no? We have seen that current was, in case of pure inductor, lagging by 90 degree, in case of pure capacitor, leading by 90 degree, in case of LCR, depending on the capacitive or inductive reactance, it was either leading or lagging. Fine. So that's why this is that phase. Fine. We understand that. So this should be the solution of equation 3. Do we understand that? Do we get that? This should be a solution of this. Now if this is the solution of this, then if I put it back here, the left hand side and the right hand side should be equal. That is what solution means after all, is it not? So let us first of all find out what is dq by dt. dq by dt will be what? Omega qm cos omega t plus theta. Is it not? This is fourth. And d2q upon dt square is equal to omega qm. Okay, cos becomes minus sine, so this minus I am writing here, and sine omega t plus phi plus theta here, and another omega comes out, so this becomes this. Is it not? Fine. Do we get that? Now I put 4 and 5 and obviously this. So is it not? Okay. So let me do this. Let me name this set of equations as 4. Fine. That's better. All these 3 together are 4. Now what happens? You don't know what kind of trouble will come later. So let us name this as 4, this as 5, this as 6. Okay. So what I am doing, putting the value of 4, 5 and 6 in 1 we get, okay, in 1, not in 1, in 3. What do we get? We get L multiplied by this. So this becomes minus omega square LQM sine omega t plus theta. Is it not? This I have put here. Plus R into this omega qm cos omega t plus theta. Is it not? Plus q upon c. So plus qm sine omega t plus theta upon c. That is equal to Vm sine omega t. Fine. We understand that? Okay. Now what I do, I try to take out omega qm from here. Okay. So it becomes omega qm, fine, omega qm into r cos omega t plus theta. Is it not? If I take out omega qm from here, you understand? How do I do that? There is no omega there. So I multiply the above and below by omega. Is it not? So here what I do, I multiply this by omega, I divide this by omega. So what happens? If I have taken out this omega qm, then I am left with 1 upon omega c. Is it not? So it is plus 1 upon omega c sine omega t plus theta, and I am left with omega qm gone, so minus omega l. So minus omega l sine omega t plus theta. Correct? Now I know we know that 1 by omega c is equal to xc and omega L is equal to XL. Okay. So what does it become? It becomes, it implies that omega qm into r cos omega t plus theta plus this is xc and this is xl. So xc minus xl sin omega t plus theta. Is it not? Do we understand that? Now this one of, see what happens, this is cos of some angle and this is sine of some angle. You were taught a skill in class 11th while doing physics of waves and oscillations. I do not know whether you remember, so I reproduce it here. If I have something like this, a cos theta plus b sin theta, then a way in which it can be simplified is by dividing it by dividing this by sum of the square of coefficients and root of that, root of the sum of square of the coefficients, which is root over a square plus b square here, and here root over a square plus b square. And to nullify this, so you understand, a cos theta plus b sin theta, I am trying to express it like this. This into root over a square plus b square. That's quite possible. Why do I do that? Because you see, if I say this is cos phi, a upon root over a square plus b square is cos phi, and I say b upon root over a square plus b square is sin phi, then what happens? Cos square phi plus sin square phi is equal to a square upon a square plus b square, square of this plus b square upon a square plus b square, which is a square plus b square upon a square plus b square, which is 1. This is what it should be. Also, you'll realize one thing, that rightly cos phi is less than 1 and sin phi is also less than 1. Okay? Which should be the case. So you understand. So what am I able to write this as? Therefore, a cos theta plus b sin theta becomes equal to root over a square plus b square into cos phi cos theta sin phi sin theta. So this becomes a square plus b square into cos of theta minus phi. You get it? So what has happened? Two similar cos and sin terms, if they are spread in an equation, they are nothing but together when added up they actually form a sinusoidal wave or cosinusoidal. Sinusoidal and cosinusoidal are the same. Fine. We understand. Okay.